Hi, I'm Cassie, and I'm going to walk you through question one of the physics pack here. Okay, so what is the question asking? Well, it says how much time will pass before there are a certain number of radioactive nuclei remaining. So this is a half-life question. I know it doesn't directly ask half-life, but it's really asking you to figure out how many half-lives have passed before this amount is remaining, and then translate that number into a number of years. And so I'm going to walk you through a structure, a table you can build that will help you solve any half-life problem like this you come across on the MCAT without using any equations. So you might have seen a bunch of equations in books like Kaplan. Forget about those. You don't need equations for half-life problems on the MCAT. You just need a basic conceptual understanding, right? And so what is that conceptual understanding? Well, what is half-life, right? Half-life is the concept that radioactive substances are unstable. And we know that unstable things, they don't stay that way for very long, right? Things like to go from unstable to stable. So over time, those radioactive nuclei are going to decay. They're going to change into something that's more stable, right? And so you can think of this as if you start with a bowl of 100 M&Ms, or in this case, if you start with 100 radioactive nuclei, right? After some amount of time passes, you're going to have only half of that original bowl of M&Ms left, right? So if you had 100 to start, you'd have 50 after some amount of time has elapsed. And that amount of time it takes to get to half the original amount is called half-life. In this case, the passage tells us that we start with 60 million radioactive nuclei. Okay, so first thing I'm going to do in these problems is I'm going to build a table. And what are going to be my columns in those table? Well, I'm going to have the amount is going to be my first column, and that amount is going to be the amount of nuclei, right? I'm also going to have my number of half-lives, and then my amount of time that's passed. And my last column is going to be my fraction remaining, or you could say percent remaining. Okay, and so we just said that we started with 60 million radioactive nuclei. So that's going to be the first input in our table here, right? And we don't want to, of course, write 60 million with all 7 zeros there. We're just going to write that in scientific notation as 6 times 10 to the 7th. And if you need to review scientific notation, you can check out my separate video on that. Okay, so we've got 6 times 10 to the 7th starting after 0 half-lives or 0 amount of time has passed, okay? And 100% or 1, right? We have everything still remaining because nothing has decayed yet, no time has passed, okay? But then after 1 half-life has passed, then the passage tells us that 1 half-life is equal to 430 years. So I'm going to write 430 here, and it's helpful to specify your units here because problems could be in minutes, hours, seconds, days, etc. So this is 430 years have passed. Then we know that whole idea of a half-life is we have half of our original amount left, right? Okay, so if we take half of 6 times 10 to the 7th, all you have to do there is half that first number. Okay, so we have 3 times 10 to the 7th left, but is that how much we're looking for? No, we're looking for a much smaller number. So we're going to keep adding on and going through half-lives here. So after 2 half-lives have passed, then that would be 860 years, 430 times 2, right? And we'd have a fourth of our original amount remaining, right? Because this is just like a pie, right? Fractions. So we had our whole pie, our whole amount of radioactive nuclei at first. And then after 1 half-life, we had only half of that pie left. After 2 half-lives, we have half of the half left, or a fourth. So we only have a fourth of our pie left here, right? And then we're going to take half of that 3. So we're going to have 1.5 times 10 to the 7th amount of nuclei left, okay? After 3 half-lives, we're going to take what's 430 years times 3. That would be 1,290 years have passed, right? And we have a half of a fourth left, which is going to be an eighth, okay, of our original amount left. So here, if we take half of 1.5, we get 0.75 times 10 to the 7th. But we know that's not proper scientific notation, right? Because has to be a whole number between 1 and 9. And so we have to move that decimal point 1 place to the right here, right? And remember the abbreviation LARS always, if we move our decimal point to the left, L, right? Then we add to our exponent. If we move the decimal point to the right, then we subtract from our exponent, right? So in this case, we moved our decimal place one place to the right, so that 0.75 became 7.5. So we're going to subtract from our decimal here, and this is going to become times 10 to the 6th there, okay? So we've got 7.5 times 10 to the 6th. Okay, so we have 7.5 times 10 to the 6th nuclei remaining. Let's keep going. All right, so after 4 half-lives have passed, that would be the equivalent of 430 times 4 years, which would be 720 years. And we'd have a half of an eighth left, or a 16th left. And if we take half of 7.5, we get 3.75 times 10 to the 6th. Notice that is exactly what the question's asking. It's asking how much time has passed until we have this amount left. So we're looking for time in terms of years, and we can see that in our answer choices. And so 720 years have passed. Of course, this question could have been worded differently. It could have asked how many half-lives have passed until we have that amount of nuclei remaining, and then the answer would have been 4 half-lives have passed, right? Or it could have been worded what fraction of the original amount is remaining, and then the answer would have been 1/16. So pretty much with any of these half-life problems you're going to come across in the MCAT, if you build a table like this, you're going to be able to figure out the answer you need to know. Now, sometimes you're not going to work linearly like this, where we started with the initial amount, because sometimes we might not know the initial amount. You might have to work backwards, right? So we could have worked from this backwards, like if we knew that we had this amount remaining after 4 half-lives have passed, we could have said, okay, now what happens if I double that amount? How much do I have? And then I'd have 7.5 if I double that amount, right? So we could have worked backwards here too. So go ahead and check out questions 22, 68, and 105 from the physics pack. They also are half-life problems, and if you use this structured approach, you should be able to figure them out. And you can also check out the section bank, Chem and Phys section, passage 8, number 60 is a great half-life problem. So thanks for watching. I hope this helped. Drop a comment if you have any questions.